jump back in. So we're discussing Lenz's law, and Lenz's law is a way of getting the direction of current flow that causes the EMF right. And as I said, there's two ways you can think about it. One is in terms of the outcome, which is the magnetic field changes, and the other one is in terms of the origin, which is the magnetic flux changes. But in both cases, the system, the EMF that you are inducing, acts in whatever direction is required to cause a nullification or a cancellation of the change that you are making. So if you are trying to create a system where you put more magnetic flux lines through a coil, the EMF will react by creating a current which creates flux lines that cancel out the new flux lines going in. If you're trying to reduce the number of flux lines going into a coil, it will create an EMF which creates a current which adds EMF lines for the ones that you take away. So it's going to basically always try and keep you at this status quo. It can never do it completely, eventually loses out, but it kind of slows down any change. That's basic. So here's an example. We're going to talk about flux lines. So here's an example. We have our good old we have a good old system where we have a loop, and we can slide our rod. And in this case, we're sliding our rod to the right. So my question is, are we increasing the area or decreasing the area? And we're increasing the area. The area of interest is the area inside the loop, which is this guy. And what that means is that we go from having 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 flux lines of magnetism going into the loop. So we have, let's move that across. Now we have 20 flux lines of magnetism going into the loop. So we increased our flux lines going into the loop by 8. And what the Lenz's law says is, oh, I'm going to create an EMF which creates a current, which creates a magnetic field, which is in such a direction that I cancel out that change. So I want to have an additional 8 flux lines, not going into the page because you just did that. I'm going to make 8 new flux lines coming out of the page. Or at least as many as I can. So you increase the number of flux lines going into the page. I'm going to respond by making flux lines coming out of the page. And how do I do that? Well, I recall that when I have a current flow in a wire, the magnetic field goes in a clockwise direction. I use my thumb as the current, and my fingers are my magnetic field line, and they go from north to south. So if I have a piece of wire like that, and I imagine cutting it, just like cut it like a piece of paper, and I can see, oh, that is going into the page on that side, and this is coming out of the page on that side. Can you see that? So if I were to do that on that side, if I was to say let the current flow in that direction, then truly I would get that flux line coming out because I'm putting that flux line in, and that guy there, and of course if that's going in that direction, this is my current, then I get that there, and that there, and that there, and that there, and so on. So what this tells you is the current that you induce will flow in a counterclockwise direction to cause additional magnetic flux lines to come out of the page to cancel out the additional flux lines going into the page that you added by increasing the area. So boom, boom, boom. If I do this one, I go from having 12 flux lines going into the page to having only 8 flux lines going into the page. So the system responds by, oh, you just took 4 flux lines away. I'm going to respond by making those 4 flux lines back. Doesn't matter where I draw them. The way I get that is I have my wire. Now, if I have my current flowing in that direction, that means that I go like that, which means here it's coming out towards me and here it's going back into the page. Oh, so my current now is going to go in that direction, and that direction, and that direction, and that direction. And I get the effect I want. And so we say current flowing in the loop increases the magnetic flux that offsets the change in flux caused by creating the larger loop area. We do that in both cases. I can imagine doing the same thing with bar magnets. Here's my loop. Here's my bar magnets. Think of the bar magnet as being like almost like a feather duster with, you know, little hairs coming out. So when you're a long, long way away, only a few of these guys go through. But when you're here, all of them goes through. So as you move the magnet backwards and forwards, you change the amount of flux going through. If I move this north-south bar magnet so it's approaching the coil, then basically it's good to draw a picture before and a picture after, and it's good to have a recollection of where you looking from. So I'm going to look from that direction. There's my eyeball looking. There's my eyelashes. I'm looking in that direction. And what I would see when I'm a long, long way away is I would see maybe a couple of flux lines, and they would be going into the loop. And then when I'm close by, I see a lot more flux lines going into the loop. So as viewed from the left-hand side, I have seen an increase in the number of flux lines going into the page. And so Lenz's law says I must create flux lines coming out of the page. Let's do that in purple. And so I want to create, to cancel out, I want to create flux lines that look like that to cancel out. And the secondary issue is, how do I do that? And I think back about this and I go, okay, there's my wire. If I have the current going in that direction, then I get that. And that's going into the page and that's going out of the page. So let's have a look. Oh yeah, I want my current to flow in that direction. I put my thumb on there and I put my thumb on there. Whoops, did it completely wrong. I want my current. Notice how I realized I'd gone completely wrong when I actually did the physical part of it. So I want my flux, I want my current to go in that direction. Yep. If the North Pole is pulled out, I go from initially I have a lot of flux lines going into the page. So when I'm at a later time, this is much further away, so I have fewer flux lines going into the page. So then I say, oh, I want to create more flux lines going into the page. And the way I get that is I do my current in that direction. So there's like 3 skills, isn't there? The first skill is, can you decide what flux line direction is? So can you look at this north-south magnet and realize the flux lines come out of the North Pole, and so they're going to go in that direction? And the second is, can you envisage if you get an increasing number of flux lines or a decreasing number of flux lines? And then the third is, do you know what Lenz's law says? Oh, Lenz's law says I'm going to undo the change. And the fourth skill is, if you know what to create, do you know how to create them using current? So, boom, 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 boom. Yeah, 4 bits.
Isn't these last 2 pictures the same?
In this case, the current goes in a counterclockwise direction. In this case, the current goes in a clockwise direction.
Oh, the direction.
Well, and also, in this case, I created flux lines which were going out of the page, and in this case I'm creating flux lines that go in.
Oh, I was talking about the pictures right below.
I'm not even talked about them yet. Sorry.
I just looked.
I'm reading. Okay. So, the alternative way of looking at this is to turn around and say, oh, I have a north pole that's approaching. How can I counterbalance that? I make a north pole to keep you away. Oh, I have a north pole that's leaving. How can I counterbalance that? I have a south pole to drag you back. Now, the way that current flows, if I look at a loop, and I'm looking at the north face of the loop, by using this little devilish system, I can see that, oh, in that case, the current flows in a counterclockwise direction. And for a south pole, I can say, oh, the current flows in a clockwise direction. So all I did up here, I can get using that, and all I did there, I can get using that.
But then how would you know the velocity direction from?
When the north pole is approaching, I create a north pole to keep you away. When the north pole is leaving, I create a south pole to keep you back. Now, you've got to be really careful about how are you looking at this. I'm looking at this thing from that. I'm looking towards the right. Because this coil, if I draw it on edge, I have a north pole on that side, but I have a south pole on that side, because that's the way it works. Front of a page, back of a page, you can't have one without the other. You can't have the north pole without the south pole. You just look at it from the different direction, you get the opposite. So you've got to be careful about which way you're looking. Here's an example. A bar magnet is dropped with its north pole pointing downwards. It is moving on axis towards a horizontal loop of wire as seen from above. What sense, clockwise or counterclockwise, will the induced current have? So let's do it both ways. Let's do it the simple way. North pole is approaching. What am I going to do? What pole am I going to create in this top surface? I'm going to create a north pole to keep you away. Which way does that current flow? CC counterclockwise, I. Agreed? That's the simple way. Let's do it the other way. I start off and I have only a few flux lines going into the page. As time passes, I add more. Agreed. That's what a north pole approaching does. Agreed? I want to cancel those guys out, and so I create these guys. How do I do that? How do I do that? Yeah. Using this corkscrew rule, okay? Easy, I think easy way. I think this is the easy way. I think this is the hard way. But now, in a test question, I might ask you, using flux lines, determine. Or using magnetic poles, determine. If I don't say which way, you can do whichever one you like. But I could specify, hey, I want you to show me this. Use the arguments for using flux lines. So,
Flux lines?
remember these arrows? Yeah, flux lines, yeah. This is where we're kind of going. We don't have a loop. We have, oh, and on this one, go back one. On this one, I could have you, when it's leaving, No one says it has to be approaching. Now, you've got to be careful. Am I asking you about as seen from above or as seen from below? If I asked you this and I said as seen from above for the current case, if I said as seen from above for the current case, you'd say a north pole, as seen from above. You see a south pole as seen from below. Yeah? Now imagine that I have a magnet leaving. As seen from above, this south will induce a north pole as seen from below, because the north pole is trying to be dragged back. A north pole as seen from below is a south pole as seen from above. So you've got to be careful about it's terminology, it's words. It's what exactly is this person asking? Above or below, etc. This is in a way the most sophisticated question we ask, which is we have a magnet that's approaching a coil. Notice the coil can be drawn in 4 different ways. There's one version of it. There's another version of it. There's one version of it. There's another version of it. And if you've not seen that before, that takes a bit of getting your head around. This is where the wire comes up and goes round and 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 round. And if you go home and get a piece of string and a bobbin, you find it has to go off that end. It has to come up on one side and go down on the other side. And this one, I'm winding it just the opposite direction. It goes up and it goes, as I'm looking from that left-hand end, if I'm looking towards the right, it goes in a clockwise direction, round and round and round. And so it leaves that way. This one, round and round, leaves that way. This one. So 2 different aspects, looking at 2 different winding orientations, 4 different coils. So again, you've got to be careful about this end versus that end. This says a bar magnet is pushed to the right with its south pole pointing to the right. It is pushed towards the solenoid along the axis. Now, yes, they're both approaching, but the south pole is nearer, so that's more significant. They're both approaching. The north pole also approaches, but it's farther away from the coil. So in all these, I've been saying, well, I've said, well, a south pole approaches or a north pole approaches. Well, so does the south, but the north pole is nearer, so don't be fooled by that. So the south pole is approaching. So that means I'm going to create, as looked at. So let's draw this. This is like that. If I'm looking at the end of this coil, I see a circle, and I see the wire to the right-hand side of the circle. If I'm looking down that coil in that direction. So I see a circle, I see this down there, and a south pole is approaching, so I'm going to get a south pole to keep it away. Now, at this far end, now I look at there, and I look there, and now I'm looking into this end. What I see is, I created a south pole at this end, so I've got to create a north pole at that end. Now, you don't need both of those visualizations. We've got to have one of them. If the south pole is being created at this end, which way does the current flow in that piece of wire? Imagine there's a traffic circle, and the traffic on the circle is flowing in the direction you need for a south pole. And you don't have any sharp corners on a traffic circle. You just kind of like merge in and merge out. If that's a south pole, means that current is flowing in a clockwise direction. Which way will current flow in this piece of wire? Up or down? Just follow it round. It goes around and leaves. Yeah. So that means current is flowing down that piece of wire, which means current is flowing through that resistor from X to Y.
How do
because it's a south pole. And the little thing I've learned is that tells me the direction. As I'm looking at that pole, that tells me the direction of current flow. So for south poles, it goes clockwise. For north poles, it goes counterclockwise. Yep. So now let's just double check this. If I had a south pole at one end, I have a north pole at the other end. Look at this north pole. If the current is flowing in a counterclockwise direction, this current has to merge with it, and so the current has to be flowing upwards. If the current's flowing upwards, must be flowing that direction. I get the same answer from X to Y. You don't need both of these, but you need one of them to be able to figure it out. The mistake is they'll say, oh, south, south, and then they'll draw that. And they're looking at the back side of a south, which is a north. So they've got the wrong sign on there. They've got to have you can't draw that in. So you've got to turn around and say, oh yeah, I get this. You go, this is a south, that means that I have a south there keeping it away, which means there's a north there. Oh yeah, I know how to do this. That's the way I do it. I get the direction in the end of the solenoid that I can see. As viewed from the left, what pole will, not to the left, but from the left. So you're on the left looking towards the right. As viewed from the left, what pole will be created at the left end of the solenoid? As viewed from the left, it's a south pole. Which way will the induced current flow through the resistor? And it is from X to Y. It's not hard, it's easy to get it backwards. Let's do another one. Oh. Can you ever go at that? Can you tell me, what pole? And can you tell me what direction? And just, write those down, those two answers, and then we'll talk through it. Okay, so commit to yourself. You don't have to tell me, but just commit to yourself what you think it is. Then tell your partner, what do you think? Let's talk about this then. So south pole is leaving. That induces a north pole there, because I don't want you to leave. Look at the arrow flow. That induces a current flow in that direction, which goes X to Y. So this is X to Y. This is north pole. It's not hard. It's just easy to get it backwards. Yes?
Is it in a way that goes from Y to X?
Yeah. I just basically, let's just try it. So let's say,
Does the magnet have to be the other side?
like that. So we have a south pole approaching, and so you create a south pole to bring it back, which means that current is flowing that direction, which is Y to X. Yep. South pole approaching means I induce a south pole here, not a north. South pole here means that it's clockwise flow, not counterclockwise. And because the wires are in the same positions, that means it's an upwards direction on that. That's one way, yeah?
Doctor,
You comfortable with that? Yep.
if you were to switch the magnet, but it does the same thing, change the direction.
I did just change the direction. Oh, do you mean flip it?
Yeah.
Yeah, that would reverse things. I could even just do this. I could even turn around and say, okay, everything's the same, except that I'm going to have my wires like that. So now, South Pole is leaving, you create a North Pole. That creates a counterclockwise current flow, which means because this is now on the right-hand side, that means the traffic has to go like that. That's y to x. Yeah? I got the same pole, but here the wire was connected on one side, and here the wire is connected on the other side.
So you flip it for the
Okay? So I can mix these up. There's no preferred direction. Okay. Cool. Let's get out of here. Okay, generalized form of Faraday's law. Let's have a look. Consider a conducting ring in a uniform magnetic field. Work done in moving the test charge once around the ring is Q times the electric field. Work done by the electric forces, the force times the distance traveled, which is, so this is Fe times d, that's the work done. 2 pi r being the circumference, and this is Q times E, that's the charge times the energy per charge. So two ways of getting the same thing. You can put them equal to each other, QE and Q big, so Q times EMF is equal to Q times electric field times 2 pi r. So rearrange my electric field equals my EMF over 2 pi r. And if I remember that EMF is equal to minus d phi by dt, this gives me that E is equal to E over 2 pi r, which equals minus d phi by dt over 2 pi r, which gives me the E dotted with 2 pi r, 2 pi r to the side. E multiplied by 2 pi r is equal to minus of E d phi b by dt. So the integral of E dot ds, because 2 pi r is the integral of ds, is equal to minus d phi b by dt. That's another law. This means that induced electric field is non-conservative. That is, the line integral of E dot ds is not equal to 0. Okay. And then we go to Maxwell's equations. So we did this. What was this called? Whose law was that? We had Q in. Gauss's law. This was, of course, a dot product. Shame on me. And this is magnetic Gauss's law. We didn't do much with magnetic Gauss's law because the answer equals 0. And then we had, well, we just had generalized form of Faraday's law, which is E dot ds is equal to minus d phi b by dt. And then we have basically, remember for the, what was it, Ampere's law? Was it B dot ds?
Yeah.
Line integral of B dot ds equals mu naught times I. And we had that problem with, remember the capacitor, and we needed to invent this, what's the word for it? It was like this, it was the end of last chapter. It was this like discharge field. Remember we had the magnetic field and we had the capacitor, and we said, well, if we take a loop like that and we have our surface going like that, we'll get one answer. And if we have our loop like that and we have that, that's another answer. So
Okay, 4 sides.
it's so anyway, so this is a variation of that. We got to that bit last time, and this little bit was added on. Discharge capacitance. Look at the back of last chapter.
I got you, though.
Okay, so we have 4 of these things. Okay, and then we have forced Lorentz law. Basically, the electrostatic force and the magnetic force. Don't care. It's there, you know. Just know they exist, because you're going to do a lot more about it next time. Next class. Next course.